Okay, guys, this is going to be our first video of several videos, maybe as many as 8, covering topics related to energy. Energy is an enormous topic in physics, and we're going to be looking at it from a variety of different perspectives. And we're going to start today by thinking a little bit about this second word here, work, but I'll get to work in a minute. I think we should start by defining energy, making sure that we have some kind of a way of understanding what energy is. And energy is like it's actually a pretty hard word or concept to define, I think, in physics. The way I'm going to define it right now, kind of provisional definition that's not totally satisfying, but I'm going to think about it as the ability to apply a force. So if an object, for instance, has energy, it has the ability to apply a force. Maybe just to think about this in a little bit more of an everyday level, if I were to go for a run, while I'm running, I am applying forces. My feet are hitting the ground and the ground is pushing back. In order to move forward, I have to push on the ground. I have to apply a force. And to apply these forces over and over again, to go for a run requires energy, which is why if I go for a very long run, I'm tired because I will have used a lot of energy in the process of going for that run. So that's one sort of just kind of intuitive, everyday way of thinking about energy as the ability to apply a force. Now, it turns out there are lots of different types of energy, and we are going to be specifically thinking about a subset of energy, which is called mechanical energy. Which is distinct from a lot of other forms of energy. Mechanical energy is the energy associated, this is energy associated with moving masses. Associated with moving masses. So for example, if I were to drop a brick on my foot, it would hurt. Why? Well, it would hurt because the brick would be applying a force to my foot. And why is it applying a force, or how is it that the brick has the ability to apply a force? Well, that's because it has energy. It has mechanical energy because it has mass and it's moving. So that's an example of what we would call mechanical energy. Now, I will just note that there are lots of different types of energy. Thermal energy, light energy, electrical energy, just to name a few. There are many, many different types of energy, but we are really going to constrain ourselves to just thinking about this particular type of energy, mechanical energy. Later on, we'll learn that there are 2 different types of mechanical energy, kinetic energy and something else called potential energy. I'm not going to go into those too much right now, or I'm not going to go into them really at all right now because we're going to focus on another thing today. But I will note that shortly, in a couple of videos or so, we're going to talk about kinetic energy. So that will be with us soon. Potential energy will be a bit later. So the thing I want to start talking about in this video more is the second word at the very, very top here, and that is work. What is work? And work, the way I want to think about work is that it is how we transfer energy. So it's about transferring energy. And by transferring, I mean from one object to another. There is another sense of work in which you can be transferring energy from one form to another, but we're only talking about this form of mechanical energy. So transferring energy from one object to another. So for instance, you could imagine a golf ball is sitting on a tee. It has no energy. It's not moving. But if I then hit the golf ball and the golf ball starts to move, now the golf ball has energy, right? That golf ball now clearly has energy because if the golf ball hit you, it would hurt. So how did I give energy to the golf ball? I did work, or specifically the golf club did work to the golf ball. And so that's going to get us to another definition or a more precise definition of work. And that is, you do work when you use a force to move something. So for instance, the golf ball or the golf club exerts a force over the golf ball, moving the golf ball. And it's the fact that it's using the force to move the golf ball that allows it to do work. So provisionally, I'm going to start us off here by saying work is defined as the force on an object multiplied by the distance that force acts. Force times distance. I'm not gonna put a box around that yet because we're gonna add to that definition a little bit later. But I will note here that the unit for this, you could think of it as newtons times meters, but we usually use the unit joules. Joules, abbreviated with the letter J. Joules, that's a unit we're going to use both for work and for energy. Since work is an energy transfer, they have exactly the same unit. So maybe before I go into that equation, that definition in any more detail, let's just think about an example. We could sort of investigate it a little bit by thinking about this example. Let's imagine I have a surface here and I have a block. And I'm going to say to you that there's a force on the block, an applied force this way, which is equal to, say, 10 newtons. We've got gravity, and let's say the weight of this block, mg, is, 50 newtons. So we've got a normal force up, which is also 50 newtons. And then imagine that there's a friction force backwards of, say, 5 newtons. And I'm going to tell you that the block moves to the right. It's going to move this way a distance of, let's make it 20 meters. So the block moves due to these forces to the right a distance of 20 meters. And what I'd like to do is to think about how much work, according to this definition, how much work do the different forces do? And you might, if you care to, pause the video and see if you can calculate what's the work done by the applied force, what's the work done by the normal force, what's the work done by friction, and what's the work done by gravity. But I'm going to go over them right now. I'm going to see if we can figure out how to do this. And I'm going to start maybe with what I think is the easiest one, which is, I think, the applied force. So we're going to find the work done by the applied force. And I think this is easy, and the reason it's easy is that the distance and the force are in the same direction. The applied force is to the right, and the block is moving to the right. So this is the case where it's actually really the simplest one. This is where I can just say that the equation is just going to be the work done by the applied force. So I'm going to say work done. We'll use W for work. The work done by the applied force is simply 10. That's the force times the distance, which is 20, and that gives me 200 joules. Now let's take a look at the work done by the force of gravity. This one's a little bit less obvious how we're going to deal with this. It is true that the force of gravity is down here 50 newtons, and it's true that the distance is 20 meters, but if you think about it, the force of gravity is down and the direction of motion is to the right, so the force of gravity doesn't actually move the block at all. And so what you might sense here, and you would be right, is that the work done by the force of gravity is actually 0 joules. And that's because, and I'll write this here, because gravity doesn't actually move the block. And that's because gravity is perpendicular to the direction of motion. And we'll get back to that. This is going to be an important concept to us, probably in the next video. If I go ahead and calculate the work done by the normal force, we're going to get the same thing. Once again, the normal force is perpendicular to the direction of motion. The object doesn't move in the direction of the normal force at all. So the normal force is also going to do no work. And the reasoning is the same as this. It's perpendicular. Okay, the normal force doesn't actually move the block at all. Maybe I'll continue over here. The fourth one that we have to do, which is maybe the trickiest one, is this friction force. So this is I'm calling this 5 newtons. This is our force of friction. So what is the work done by the friction force? And I think this is the trickiest one because the direction of the friction force is opposite the direction of the distance moved. And you might wonder how we deal with that. And it turns out what we're going to do is we're going to make the work value done by the friction force negative. So I'm going to put a negative out front. Negative 5 times the distance is 20. This is going to give me a total of negative 100 joules. So what we've learned here is that work is positive. The work value is positive. This one up here was positive. Whenever the force and distance are in the same direction, as was the case with the applied force. The work is negative anytime the force is opposite the direction the object moves. So that was the case with friction. And the work done is 0 anytime the force is perpendicular to the distance moved. So that was true of normal force and gravity here. By the way, I could ask the final question I might ask here is what is the total work? What is the total work? And to find the total work, what I would have to do is add up all of my answers. So I've got positive 200 plus 0 plus 0 plus negative 100. That would give me a total work. So it's going to be 200 plus 0 plus 0 plus negative 100 gives me positive 100 joules. That would be the total work. So that's all I'm going to say in this video. That's a brief introduction to work. We're using force times distance, and maybe I'll just go up here and recognize here that the only way to get a work value is we need to be multiplying somehow parallel components. Later on, I think in our next video, we're going to look at how it does rely somehow on parallel components. And that'll come up in the next video.